behavior. So first, an analysis model is built to abstract essential aspect of the application domain without regard for eventual implementation. This model contains objects found in the application domain, including a description of properties of the objects and their behavior. Then a design description are made and details are added to the model to describe and optimize the implementation. The application domain object form the framework of the design model, but they are implemented in the terms of the computer domain objects. And finally, the design model is implemented in the programming language with database and hardware. So we describe a graphical notation for expressing object-oriented models such as application domain and computer domain. Objects can be modeled, designed, and implemented using the same object-oriented concepts and notations. The same seamless notations are used from analysis to design to implementation so that the information added in one stage of the development need not be the lost or translated for the next stage. So what is object oriented? Generally the term object oriented means we organize software as a collection of discrete objects that incorporate both a data structure and behavior are only loosely connected. There is some dispute about exactly what characteristics are required by an object-oriented approach, but they generally include four aspects: identity, classification, polymorphism, and inheritance. So, what are the characteristics of objects? Identity. Identity that the data is organized into discrete or different which are distinguishable entities called objects. Example, a paragraph in a window, a paragraph in a document, a window on my workstation, the white queen in chess game are the examples of the objects. The objects can be concrete, such as a file in a file system, or conceptual, such as scheduling policy in my multiprocessing operating system, and each object has its own inherent identity. In other words, two objects are different even if their entire attribute values are identical or same. So the second is a polymorphism. Polymorphism means the same operation may behave differently on different classes. The move operation, for example, may behave differently on different classes. The operation is an action or transformation that an object perform or is a subject to write, justify, display, or move. These are the examples of operations. Operation is an action that transformation that can object perform. A specific implementation of operation by a certain class is called as a method. A specific implementation by an operation for a certain class is called a method because an object oriented operator is polymorphic. It may have more than one method implementing it. So modeling concept, not implementation. So most of the effort to date is in object oriented community has been focused on programming language issues. The current emphasis in the literature is on implementation rather than analysis and design. Object oriented programming languages are useful in removing restrictions due to inflexibility of traditional programming languages is in a sense. However, this emphasis is a step backwards for software engineering by focusing excessively on implementation mechanisms rather than underlying thought process that they support. So, object oriented development is a conceptual process independent of programming language until the final stage. Object oriented development is a fundamentally a new way of thinking, not a programming technique. Its greatest benefit come from the helping specifier, developer and customer express abstract concepts clearly and communicate them each other. It can serve as a medium for specification, analysis, documentation and interfacing, as well as for programming. Even as a programming tool, it can have various including conventional programming languages and databases as well as object-oriented languages. So we present a methodology, we present a methodology for object-oriented development and a graphical notation for representing object-oriented concepts. The methodology consists of building a model of an application domain and then adding implementation details to it during the design of system. We can call this approach the object modeling technique, that is OMT, and this methodology has following stages: analysis, system design, object design and implementation. So first we will see analysis. Analysis, starting from a statement of problem, the analyst build a model of real world situation showing its important properties. The analyst must work with a requester to understand the problem because problem statements are rarely complete or correct. So sometimes the problem statements are ambiguous, vague, unclarity, there is no clarity. So first we should have to analysis what is the problem statement, what is the requirement and what is the object and what will be the output of this project. So this analysis part is the most important. The analysis model is concise, in short, precious abstraction of what is the desired system must do, not how it will be done. So this object in the model should be implementation domain concepts and not a computer implementation concepts such as a data structures. A good model can be understood and criticized by application experts who are not programmers. The analysis model should not contain any implementation decisions. For example, a window class in a workstation windowing a system would be described in terms of attributes and operations visible to the user. Second is a system design. After analysis, the part is second part is system design. So system designer makes high level decisions about overall architecture. During the system design, the target system is organized into subsystems based on both the analysis structure and proposed architecture. The system designer must decide what performance characteristics to optimize, choose the strategy of attacking the problem, and make tentative resources associations. For example, the system designer might decide that changes to the workstation screen must be fast and smooth Even when windows are moved or erased, and select an appropriate communications protocol and a memory buffering strategy. This is the example regarding the system designer. System designer makes high level decisions about overall architecture. During the designing system, he must or she must consider the what are the requirements and what is the output, what is the problem statement. So system designer must decide what the performance of characteristics optimize, select the strategy of attacking the problem and to make tentative resource allocation. Then third part is object design. The object designer builds a design model based on the analysis model but containing implementation in detail. The designer adds details to design model in accordance with the strategy established during the system design. The focus object design is the data structure and algorithms needed to implement each class. The object class from analysis are still meaningful, but they are augmented with computer domain data structure and algorithms selected to optimize important performance measures. Both application domain objects and computer domain objects are described using same object-oriented concepts and notations, although they exist on different conceptual plans. And fourth part of the this is implementation. The object classes and relationships developed during the object design and finally translated into particular programming language, database or hardware implementation. Programming should be a relatively minor or mechanical part of development cycle because all of the hard decisions should be made during the design. So during implementation, it is important to follow good software engineering practice so that a traceability to design is straightforward, and so that implemented systems remains flexible and extensible. So traceability, while implementing a project, traceability is the most important concept to forward direction as well as a backward direction. Whenever we develop a project, so by the traceability we can go to the problem statement and solve each and every problem regarding each and every requirement. And traceability, due to traceability, the implementation of your project is very efficiently. So then object oriented concepts can be applied throughout the system development of life cycle from analysis through the design to implementation. The same classes can be carried from stage to stage without a change of notation, although they gain additional implementation details in the latter stages. Although the analysis view and the implementation view of window are both correct, they serve different purposes and represent a different level of abstraction. Different level of abstraction. The same object oriented concepts of identify, classification, polymorphism, and inheritance apply through the entire development cycle. Some classes are not part of analysis but are introduced as a part of design or implementation. For example, data structures such as a tree, hash tables, and linked list are rarely represented in the real world. They are introduced to support a particular algorithm during design, and such data structure objects are used to implement real world objects within a computer and do not derive their properties directly from real world. So OMT methodology uses three kinds of models describes, that is object model, dynamic model and functional model. The object model describing the objects in the system and their relationships. The dynamic model describing the interactions among the objects in the system, and the functional model describing the data transformation of the system. Each model is applicable during all stages of development and acquires implementation details as a development progresses. A complete description of system requires all three models. So object model describes the static structure of object in the system and their relationships. Object model contains object diagrams. An object diagram is a graph whose nodes of object classes and asks a relationship among the classes. The dynamic model describes the aspects of a system that change over time. The dynamic model is used to specify and implement the control aspects of a system. The dynamic model contains a state diagrams. The state diagram is a graph whose models are states and whose arcs are transitions between states caused by the events. The functional model describes the data value transformations within a system. The functional model contains data flow diagrams. The data flow diagram represents computation. The data flow diagram is a graph whose nodes are processes and whose arcs are data flows. The three models are orthogonal parts of the description of complete system and are cross-linked. The object model is most fundamental, however, because it is necessary to describe what is changing or transforming before describing when and how it changes. So the differences from functional methodology. The object-oriented development inverts previous functional-oriented methodology as exemplified by methodologies. Primary emphasis is placed on the specifying and decomposing system functionalities. Such an approach might seem the most direct way of implementing a desired goal, but the resulting system can be fragile if the requirement change. A system based on decomposing functionality may require massive reconstructing, that is restructuring. By contrast, the object-oriented approach focuses first on identifying objects from the application domain, then fitting procedures around them. Although this may seem more indirect, object-oriented software holds up better as the requirements involve because it is based on underlying framework of application domain itself rather than the ad hoc functional requirements of a single problem. So modeling as a design technique. A model is an abstraction of something for the purpose of understanding it before building it. Because a model omits non-essential details, it is easier to manipulate than original entity. Abstraction is a fundamental human capability that permits us to deal with complexity. Engineers, artists, and craftsmen have built models for thousands of years to try out designs before executing them. Development of hardware and software systems is not exception. To build complex systems, developer must abstract different views of the system, build models using precise notations, verify that the models satisfy the requirements of the system, and gradually add details to transform the models into an implementation. The object-oriented modeling concepts are applied to analysis design. There are three kinds of object-oriented models composing the structure. The composing the object modeling technique. The object model which describes the static structure, dynamic model which describes temporal relationships, and functional model which describes functional relationships among the values. Then modeling. Designers build many kinds of models for various purposes before constructing things. Examples include architectural models to show customers, airplane scales models for wind tunnel tests, pencil sketches for the composition of oil paintings, blueprints of machine parts, storyboards of advertisements, and outlines of books. Models are several purposes. So first purpose is testing a physical entity before building it. The medieval masons did not know the modern physics, but they built a scale of models of Gothic cathedrals to test the forces on the structure. Scale models of airplanes, cars, and boats have been tested in the wide tunnels and water tanks to improve their aerodynamics. Recent advances in computation permits the simulation of many physical structures without having to build physical models. Not only is simulation cheaper, but it provides information that is too fleeting or inaccessible to be measured from a physical model. Both physical models and computer models are usually cheaper than building a complete systems and enable flaws to be corrected early. Then next part is modeling, communication with customers, architects, and product designers build a model to show their customer. Mockups, the demonstration products that imi- imitate some or all the external behavior of systems, such as visualization. Storyboards of movies, television shows, and advertisements allows the return to see how the ideas can flow. Awkward, awkward transitions, dangling ends, and unnecessary segments can be modified before detailed writing begins. Artists' sketches allow them to block out their ideas and make changes before committing them to oil or stone. Then reduction of complexity in modeling. Perhaps the main reason of modeling, which incorporates all the previous reasons, is to deal with systems that are too complex to understand directly. The human mind can cope with only limited amount of information at one time. Models reduce complexity by separating out a small number of important things to deal with the time. So Object modeling technique. We find the useful model a system from three related but different viewpoints, each capturing important aspects of the system, but all the required for a complete description. So, object modeling technique is a name for the modeling methodology that combines three views of modeling systems. The object model represents static structural data aspects of a system. The dynamic model represents temporal behavior control aspects of system. The functional model represents the transformal function aspects of system. So a typical software procedure incorporates all three aspects. It uses a data structures, that is object model, its sequence operations in time, that is a dynamic model, and transforms their values, that is a functional model. Each model contains references to entities in other models. For example, operations are attached to objects in the object model but more fully expanded in functional model. So object model describes the structure of objects in system, their identity, their relationships to other objects, their attributes and their operations. The object model provides essential framework into which the dynamic and functional models can be placed. Changes and transformations are meaningless unless there is a something to be changed or transformed. So our goal in constructing an object model is capture those concepts from the real world that are important to an application. In modeling an engineering problem, the object model should contain terms familiar to engineers in modeling a business problem, the terms for business, and in modeling a user interface terms from the application domain. The analysis model should not contain computer constructs unless the application being modeled is inherently a computer problem, such as a compiler or an operating system. The design model describes to solve problem and may contain computer constructs. The object model is represented graphically with object diagrams containing object classes. Classes are arranged into hierarchies sharing common structure and behavior and associated with other classes. Classes define the attribute values carried by each object instance and the operations which each object performs undergoes. Then dynamic model. The dynamic model describes those aspects of system concerned with time and sequencing of operations, events that mark states that define the context for events and the organization of events and states. The dynamic model captures control that aspects of a system that describe the operations that behavior without regard for what the operations do, what they operate on, and how they are implemented. Dynamic model is represented graphically with the state diagram shows the state and event sequences permitted in a system for a class of objects. State diagrams also refers to the other models. Actions in state diagrams correspond to the functions from a functional model. Events in state diagrams become operations on objects in object model. Then third part is functional model. The functional model describes those aspects of system concerned with transformation of values, functions, mappings, constraints, and functional dependencies. The functional model captures what a system does without regard for how or when it is done. The functional model is represented with data flow diagrams which shows the dependencies between the values and the computation of outputs from the input values and the functions without regard for when or when or if the function are executed. The traditional capturing concepts such as expression trees are examples of functional models, as are less traditional concepts such as spreadsheets. Functions are invoked as actions in the dynamic model and are shown as operations on objects in object model. Then what is the relationship among models? Each model describes one aspect of system but contains references to other models. The object model describes a data structure that the dynamic and functional models operate on. The operations in object model corresponds to the events in the dynamic model and functional model functions in the functional model. The dynamic model describes the control structure of objects. It shows the decisions which depends on the object values and which cause the actions that change object values and invoke the functions. The functional model describes the functions invoked by operations in object model and the actions in dynamic model. Functions operate on data values specified by object model. The functional model also shows the constraints on the object values. There are occasional ambiguities about which model should contain piece of information. This is natural because any abstraction is only a rough cut at a reality. Something will inevitably spread the boundaries. Some properties of system may be poorly represented by models. And this is also normal because no abstraction can capture everything. The goal is to simplify the system description without loading down the model with so many constraints that it becomes a burden and not a help. For those things that the model does not adequately capture natural language or application specific notation is still a perfectly application tool. So this is the end of the introduction of fourth chapter.